In this lecture, we're going to take a deeper dive into energy diagrams and look at how we can use them in a more useful manner, I guess, when we're looking at chemical processes. So what I want to start with is taking two energy diagrams. So two graphs where along the y-axis in either case is free energy, and that's a quantitative value. That's an actual number. Whereas the x-axis is a little bit more vague, and that is reaction coordinate. Now, what reaction coordinate is basically how far along you are in the axis. And it turns out that positive and negative values don't mean so much, because what you do is you draw your curve, which, if you recall, is a potential energy surface. And then you have to start defining components. Just from what I've drawn so far, and that other one looks a little sloppy, excuse me, I'm gonna go, oh, that's not what I wanted to do. Yeah, it still looks weird. I don't know why. Drawing them like that's kind of weird to me. Sorry, I'm struggling here. There, okay. So it's just the mirror image of the opposite of the one on the left. Anyway, what I'm getting at, sorry, got a little sidetracked there, is that from the data I've given you so far, you can't know too much about the reaction. We need to actually write in some actual details on top of the potential energy surface to make sense of it. Now, for example, I'm going to start by defining both ground states as either SM for starting material or P or product for product. Now, in both cases, I put the starting material as the left ground state, which again is the valley in our potential energy surface, and then the product as the right ground state. Now, it doesn't have to be that way. I could have flipped them around, whatever's kind of most convenient for you to communicate the energetics of your chemical process that you're looking at. Now, in both cases, we have one hill, and we'll look in the next lecture at multiple hills, and the one hill is our TS, or transition state. A transition state is always a hill that separates two valleys. It's always kind of a midway point between two ground states. I don't like to use the word intermediate, because intermediate is another type of ground state that we could look at. Okay, so TS, again, is transition state. Now, what I want to ask about these two reactions, we have the left reaction and the right reaction, or process, however you want to say it. I'm going to call them reactions. I mean, they are. We have a left one, a right one. I'll name one A and B. So classify, what I want you to do now for a question is classify reaction A and B as spontaneous or not spontaneous. Okay, now I'm going to go, here, I'll just zoom out. So that is it's not really a question, but a task. I'll put question marks around it so you know that's a fair thing that I could ask you on an exam, is looking at these two energy diagrams for these chemical reactions, can we designate either as being spontaneous or not spontaneous? If we think back to the lecture where we talked about spontaneity in chemical processes, we said that spontaneous processes are those where once you initiate them, the reactions keep going and keep going until the limiting agent has been fully consumed. So combustion was a really good example, where we have oxygen in excess in most cases on this planet compared to our fuel source, which might be octane if we're burning things in a car. And so the reaction is going to kind of keep going and keep going and keep going. I guess if it's in a car, there's a fuel injector to control how much fuel gets dialed in, so we don't just run out of, so we can kind of govern how fast our cars go. Anyway, so we had that kind of cumbersome, but accurate, but cumbersome definition of spontaneity. But there's a more precise definition that might be more helpful, and that is when the delta G of reaction is less than 0. That is to say, i.e., the change, which again is our delta, or that triangle, the change in free energy, which is G, for the reaction, which is starting materials to products, is negative. I have a lot of parentheses there, so this will bug me unless I get rid of that first one. Okay, so delta G RXN, delta G of reaction is less than 0. Say that a different way. The change in free energy, change is the delta, which is the triangle. Free energy is the G, that type of energy that we use, which has a combination of enthalpy and entropy. For the reaction, which is the conversion of starting materials onto products, okay, is negative. So we just look and we see, is the difference in free energy between starting materials and products negative? Whoop, I have my eraser out. Sorry about that. Okay. So is the does, and really what it's saying is, does the free energy decrease from starting materials to products? Now, if we ask that question, it's actually a fairly easy one to answer once we're looking at the energy diagrams. At first, though, it might be a little bit cumbersome, because as we traverse the potential energy landscape, we start at our starting material valley, and we have to go up in free energy, positive free energy, before we go down to products. So it's a little bit tricky maybe to think about and see, are we going down in energy or up in energy as we go from starting materials to products? We certainly go up and then down. So it turns out it's fairly simple. You kind of ignore the transition state energy altogether and just look, how does the energy of the system change as we go from starting materials to products? Okay, so got that in there. Perfect. All right, so what happens? Well, if you look, the starting material that we start with, I'm going to change the color here. The starting material has a higher y-axis value than the product. So again, we ignore that transition state energy value, and we just focus on the difference in energy between the starting material and the product. And our starting material was higher. So the delta G, the change in free energy for the conversion of starting material to products, is negative. We started higher. This is like starting on the shelf for the bowling ball, and then it just kind of tumbles down or decreases in potential energy as we go onward to product. There's a little bit of a barrier that we have to overcome, and we'll get to that in a second as we crawl over the transition state. But overall, starting material to product led to a decrease in free energy. Now, conversely, if we look at our reaction B, the starting material starts much lower than the product. The product is much higher in energy. So as we look at the change in energy, we're going to have to say that in this case, the delta G of reaction is positive. The change in free energy as we go through the reaction has increased. The free energy has increased as we go from starting material to products. Now, I know the transition state seems to always imply we'll increase the free energy before we go on to products, but we ignore the transition state when we're talking about the delta G of reaction. So to be a bit more quantitative about it, we would say the delta G of reaction is less than 0 for reaction A. In reaction B, the delta G of reaction is positive or greater than 0. And so we would say that in the first case, we have a spontaneous reaction. Whereas in the second case, we do not have a spontaneous reaction. Because we had this second definition where we said that anytime the change in free energy was negative, we had a spontaneous process. If it's 0, or greater than 0, it's not a spontaneous process. Okay, and we can't, and that again has the ramifications that we can't necessarily say that all of the limiting fuel that we provide to such a process, if it's not spontaneous, will be consumed. Okay, we might have to continuously input energy to get all of the limiting fuel to be consumed. Okay, so another question I might ask about a chemical process, and I'm going to get, yeah, I think I'll leave the reaction A and B behind now, but I want to ask, which of the, well, let's look at it this way. How do we know which reaction would be faster? Faster. Well, that implies a speed. And whenever we're thinking about a speed for a chemical reaction, we're moving away from an area of thermodynamics and into an area of kinetics. So thermodynamics, I like to use this word stability. Whenever you hear the word thermodynamics, I want you to think about stability or relative stability. But what we've looked at so far is energy transfer. So thermodynamics is looking at energy transfer, how much energy is leaving the system during a chemical process or must be absorbed by the system as a result of the chemical process. With kinetics, we're looking at how fast that chemical process will occur. And so that's fast or slow, that's speed. And again, speed is kinetics. Okay, so how do we know this? We can determine this from the potential energy, excuse me, the energy diagram. So it can be determined from the energy diagram. And in particular, it depends on the heights, I guess, or G values, which again is the free energy, of the transition states. Okay, now in general, if it depends on the heights or the G values of the transition states, lower transition states lead to faster in its transition state energies, lead to faster reactions. And if we're going to go this far, I should call it free energies. So lower transition state free energies lead to faster reactions. So this phrase is very important. And then conversely, higher transition state free energies lead to slower reactions. Okay, so what I want to do is consider two alternative reactions. So I'm going to call this reaction C and reaction D. Okay, so reaction C and reaction D. And let's make it so the starting material energy is virtually the same and the product energy is virtually the same. So both of these reactions, if you look, the product is lower in energy than the starting material for both reactions C and D. So both of these reactions would be spontaneous. Now what I'm going to do is vary the reaction by having different transition state energy heights. So the top of the hill is the transition state. And so now that I've drawn my, and I could write reaction coordinate, it does get redundant, but it's always a good idea to label our axes. So I'm just going to call the y-axis G for free energy. Okay, so which reaction between C versus D is faster. Okay, so this is handwritten notes, but hopefully it's not a stretch to see that the difference in energy between the starting material and the transition state is higher for C versus D. So C, maybe I should have gone this way. I could say TSC is higher, and TS for reaction D is lower. So which of these reactions is faster? Reaction D is faster because it has a lower transition state energy. Now, that's all correct. That's not usually how we say it, though. Instead, what we like to do is look at the kinetics or speed of a reaction based on its activation energy. So the activation energy this is an important concept. This is the change in energy from a ground state, and this is going to usually be a starting material, or an intermediate. It's the change in energy from a ground state to a transition state. Okay. So the change in energy from a ground state to a transition state is the activation energy. I'm just going to zoom back up here, and I'm going to say that this distance here, and maybe I'll use my blue arrow again. This distance here, that is the activation energy for reaction C. It's that difference from the starting material of reaction C to the transition state of reaction C. Now, on the opposite side, that distance between the starting material and the lower transition state is going to be the activation energy for reaction D. So we said that reaction D is faster because it has a lower transition state energy. Another way of saying that is we would say the activation energy, as opposed to transition state energy, the activation energy for reaction D is lower than that of reaction C. So in the above example, I'm going to put it in the context of reaction C, which is slower. In the above example, reaction C is slower because it has a larger activation energy. Okay, so we've got, we use the transition state energy to think about how fast or slow a reaction is. And if we just look at that relative to the starting material energy, we get to the activation energy. Okay, so activation energy is determined by the transition state energy. We haven't done anything new so far by defining that term, but we could say something like, something like the activation energy is the energy required to activate a starting material to do a reaction. Okay? That's a nice term to use. Sometimes the activation energy is called the barrier to reaction. So by calling it the activation energy, we think about how much energy we have to pump into a system for a reaction to occur. This is kind of like saying if we know the activation energy is 20 kcals, that's a fairly common number. If it's 20 kcals, the 20 kcals number is kind of like a key to get the reaction to go. Okay, so we have to get 20 kcals of energy, put it into our system, and the reaction will now occur at some sort of rate that's productive. That's useful on a time scale. Okay, it's also called the barrier to reaction, which, if you think about it, is kind of a negative way of looking at it, but it's still an effective way. It can be useful in certain contexts. If the activation energy is 20 kcals, said another way, the barrier to reaction is 20 kcals, which means no reaction will occur until a good number of those molecules reach the 20 kcal energy threshold. So it's also called the barrier to reaction, which is the threshold. I mean, it's all the same, and it's all controlled by the transition state energy, but it's the threshold for a reaction to occur. Okay, so just kind of different ways of looking at how, what determines whether a reaction will be fast or slow. And it's based on how high or low the activation energy or reaction barrier is. Higher barriers to reaction under this context. So if you have if you have a higher barrier to do something, you're less likely to do it, or at least less likely to do it quickly. So higher barrier to reaction leads to slower reactions. If you think about what fast and slow is, in the context of reactions, we have like trillions and trillions, like a mole of starting material molecules, a mole of starting material molecules. If we have a higher barrier for a reaction, then there's going to be fewer of those starting material molecules that get the job done per unit of time. And speed is all about doing something for some set period of time. So per period of time, for every second, let's say, there's going to be fewer molecules that are able to accomplish the reaction if the barrier is higher. Now, if the barrier is lower, more molecules can hop over the hurdle, the reaction barrier, per unit of time. And if there's more starting materials that are jumping over that hurdle and turning into products per unit of time, it's a faster reaction. Okay, so in this first lecture, we looked at, we started thinking about kinetics. There's going to be other classes where you look at this in more mathematical detail, and we're going to look at things like rate laws and that sort of thing later on in the semester. But for now, it's really useful to just think about the rate or how fast a reaction will occur based on transition state energies, which can be reflected in energy diagrams. In the next lecture, we'll look at how things like temperature and that sort of thing impact the rate of a reaction before we move into something called catalysis and inhibition.